Hello and welcome to all students. In this lecture, we study about the least upper bound of a function and greatest lower bound of a function in the closed interval or in the given interval. In the previous lecture, we studied what is meant by bounded intervals and functions on uh, bounded and unbounded intervals. Okay, so let us we write the definition of least upper bound and greatest lower bound of a function. Or these are the notations. Okay, so let us write. So first of all, we write the definition. Definition of least upper bound and greatest lower bound. So we know the definition, we are writing the notations now. Okay, so let I be a bounded interval on R. Let capital I be a bounded interval on R, full stop. If f be a bounded function, f be a bounded function on I, defined as f, it is function from I to the set of real numbers. Okay, then we write m capital M close bracket f comma semicolon I, it is equal to, and this is the notation for least upper bound of values of function f of x belongs to I. Okay, x belongs to I. So this is our first notation for least upper bound of a function in the interval I, and we write the second is small m closed interval f semicolon I is equal to, this is notation for greatest lower bound. Okay, greatest lower bound of all values of function f of x, all values of function f of x where x belongs to I. Okay, so these are the two important notations, okay, that we will use in the further. Okay, so graphically we denote these two least upper bounds and greatest lower bound like this. So let us draw a simple graph now. we start from this point, okay, and then we draw this point to this point. So all we know, x-axis, y-axis, x-axis, y-axis always perpendicular, intersection is origin. And suppose we draw one arbitrary graph, okay, draw one graph of a function f, and suppose this is a and this point is b point, and what we have, our graph is in the interval, closed interval a comma b, okay. So what is the greatest lower bound of values of f of x? That greatest lower bound appears here at this point, and we call it is m f I, okay. Now what is least upper bound of the values of function f of x? And that least upper bound you can find by drawing the one horizontal line from this point, and it crosses to y-axis here, and that point, that value is nothing but, that number is nothing but the capital M f I, okay. So this what is here, it is our function f of x. It is defined in the interval closed interval a b, and the graph is like this, and from that graph we can show all values of function lies on y-axis. So this value is called as mfi, means greatest lower bound of function f of x, and this value is called as least upper bound of function f of x, okay. So let us try to take one particular example. Let us take one example, okay. So consider a function f defined from closed interval 0 comma 1 to the set of real numbers, and it is defined like this: f of x is equal to x for all x belongs to closed interval 0 comma 1, okay. And so if we so can you write the values of m f I? So this is least upper bound, okay, smallest of all upper bounds, least upper bound of function f of x. So least upper bound of values of f of x, and x belongs to I, okay. It is equal to, so let us call it is interval I. What is I is closed interval 0 comma 1, okay. And that value is nothing but f of 1, and f of 1 is 1, okay. So the value is 1, so we write here it is equal to 1. Now we write the value of m f I, means greatest lower bound of all values of f of x where x belongs to I, okay. And it is equal to, so greatest lower bound, all lower bounds of this set, and we find the largest value of all the lower bounds, and that largest value is again a 0. So 0 and 1, they are not member of this set, they are member of, yes, they are member of this set, but they are not, we are not taking these numbers from this set. Okay, we are taking from all the values of f of x. Okay, so let us denote graphically these two numbers now. Okay, graph is very important. So we draw y-axis. Okay, then we draw x-axis. Okay, suppose here it is 1. Okay, and again here it is 1. Okay, 0 1 on the x-axis, 0 1 on the y-axis, both are perpendicular, and our function is f of x is equal to x. It is defined in this range 0 to 1, and we know the graph of this function f of x is equal to 0, and graph is, we draw the graph of this function. Graph is like this. Okay, so this is the graph of function f of x is equal to x. So where is the value of, so lower end of that graph is here, and this point is nothing but small m. The value on the y-axis is nothing but m f I. Okay, means value is 0, and this value, upper end of that graph, we draw the one horizontal line from this point, it crosses to y-axis set here, and the value at this point is, functional value at this point is capital M F I. And has value 1. So this is the way of finding greatest lower bound and least upper bounds of the given function in the given interval. Okay, now that was very simple. Now let us go to the one more example. Let us go to the one more example now. Suppose our function, example number 2, let f is defined from closed interval 0, 2 to the set of real numbers r, and it is defined like this: f of x is equal to x square. Okay, so it is defined f of x equal to x square for all x belongs to 0, 2. Okay, so can we write, so we can write m f I is equal to, it will be 4, and small m Fi is equal to 0. So this is least upper bound, and this is greatest lower bound of the given function in the given interval 0, 2. So you can draw the graph and check. Okay, now let us go to define. Now let us define what is meant by subdivision of the closed interval a comma b. Okay, now next is definition of subdivision. Okay, So right here, subdivision, okay, of the closed interval, a closed interval a comma b. Definition. So this is the definition of subdivision. Definition of subdivision. Okay. Subdivision of closed interval AB. So we write here, let closed interval a comma b be a closed interval of R, be a closed interval of R. R means set of real numbers. Okay, full stop. By a subdivision of closed interval AB, by a subdivision of closed interval a comma b, we mean a finite subset, we mean a finite subset, like this: x naught comma x1 comma dot 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 xn of closed interval a comma b, such that a is nothing but x naught and x naught is less than x1, x1 is less than x2, x2 is less than dot dot dot, xn is less than xn, and xn is nothing but b. Okay, so subset is like this. Such a subdivision is denoted by such subdivision is denoted by a Greek notation sigma. Okay, Greek notation sigma. Thus we write that subdivision sigma is equal to, therefore we write thus sigma is equal to the set x naught x1 comma dot 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 comma xn. This is subdivision. These n numbers divides the closed interval 0 comma 1 into n subsets or into n intervals. Due to sigma, we have n number of closed subintervals. Due to this sigma, we have the n number of due to sigma we have n number of closed subintervals closed subintervals and these closed subintervals are: first closed subinterval is x0 comma x1, second is x1 comma x2, third is x2 comma x3, and comma dot dot dot, and nth closed subinterval is xn minus 1 comma xn. So these are the n subintervals. Okay, and these subintervals are denoted by first is I1, denoted by I1 is equal to x0 comma x1, I2 is equal to x1 comma x2 comma dot dot dot, and finally we denote in is equal to xn minus 1 comma xn. Okay, so these are the n subintervals and the notation for these n subintervals. And if we observe that, if I take the union of all these subintervals, then what will happen? Okay, see here. So what is I means our closed interval a comma b, and it is equal to I1 union I2 union dot 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 union in. So if I take union of all these n intervals, then we get our original interval, closed interval AB. Okay, so now let tau be the another subinterval of closed interval AB. Now let us consider the tau be another subdivision of closed interval AB. Let tau be another subdivision of closed interval a comma b, such that sigma is subset of 2, such that sigma is subset of 2. Then tau is called the refinement of sigma. Then tau is called refinement of sigma. Okay, because tau contains more points than the sigma, and sigma is subset of tau. Okay, that is tau is obtained by adding more points of subdivision of sigma. That is also very important. Okay, as tau is refinement of sigma, means tau is obtained by, that is right here, tau is obtained by adding more points, to subdivision of tau. More points into the subdivision sigma, points into subdivision sigma. Okay, that's why tau is called as the refinement. And if I take a union of sigma and tau, if sigma and tau are two subdivisions, and if I take a union of sigma and tau, sigma union tau. Okay, so sigma union with tau is also a subdivision of closed interval AB, is also subdivision, of closed interval A comma B, and it is refinement of both sigma and tau. Okay, so this union is a subdivision of closed interval AB, also it is a refinement of sigma and tau. The intervals I1, I2 up to In are called as component intervals. So the intervals I are called as component intervals. Okay, component intervals of sigma, of subdivision sigma. Okay, so sigma I means I runs from 1 to n, I subintervals. These are called as component intervals. Okay, so and what is the length of these component intervals? So here we note that modulus of IR means it is nothing but the XR minus 1, and it gives the length of rth interval, rth component interval, rth component interval IR. Okay, so this gives the length of rth component interval. Okay, that is very simple. Okay, now in this lecture we studied the least upper bound and greatest lower bound of a function, and we defined what is meant by subdivision, of a given closed interval AB, and what is meant by a refinement of the given closed interval AB. Okay, so in this way, now today we stop here. This is the end of our lecture, and thank you. Thank you.